Hi, and welcome back to Atomic Math. Today we're going to look at the kinematic equations that we use to solve kinematic questions. So first, let's look at the equations. So I'm going to list a few equations here. First one we have is the final velocity is equal to the initial velocity plus acceleration times time. The next equation is that the final position minus the initial position is equal to the initial velocity times time plus 1/2 acceleration times time squared. Then we have the final velocity squared minus the initial velocity squared is equal to 2 times the acceleration multiplied by the change in distance. We also have that the change in distance can equal 1/2 of the initial velocity plus the final velocity multiplied by time. And finally, we can find the change in distance by multiplying the final velocity by time and minusing off 1/2 times the acceleration of time squared. Now, it may seem like a lot of equations, and you may notice that some of these equations look fairly similar. So why do we have so many when it almost looks like we could only use a couple and derive the rest? So the reason being is that this setup makes it a lot easier for solving these kinds of equations. And the reason is that you're going to notice that each one of these equations is missing one term. So when you're looking at a question, you decide on what term do you need, but what term are you missing? And then that can help direct you to the right equation. So for example, this first equation, it doesn't have distance in there. So if we were working with a question and we didn't care about distance and it wasn't given to us, we would use this equation. The second equation is missing the final velocity. The third equation is missing time. The fourth is missing acceleration. And the final one is missing the initial velocity. So depending on which value is missing from the story and you don't need to find it in the answer, this will tell you which equation to choose. So let's take a look at a question. A car begins driving from a stationary position. It accelerates at 4 meters per second squared for 12 seconds, and then it travels at a steady speed for another 15 seconds, all in the same direction. How much distance has the car traveled? First thing we want to do is draw a diagram so we can see what we're talking about. So we have a car. It's going to accelerate for 12 seconds, and then it's going to drive at a constant velocity for 15 seconds. So we don't know how much distance it's going to cover, but we do know that the distance 1 is during the acceleration, and the distance 2 is going to be during the constant velocity. So let's start by looking at what's happening in the first 12 seconds. We're going to use this equation here because I don't know the final velocity when I finish accelerating. So I'm going to use the equation that doesn't require it. So in this equation, we can see that the distance traveled will be the initial velocity multiplied by time plus 1/2 times the acceleration and then time squared. Now, of course, our initial velocity is 0, so that first term is just going to disappear. So we're really just going to have 1/2 times 4 meters per second squared times 12 squared. So our initial distance during that acceleration is going to be 576 meters. So our x1 will be 576 meters. Before we can work on the constant velocity section, we need to determine how fast were we going when we finished our acceleration so we know what this constant velocity will be. So we can use this equation now because we know our initial velocity was 0, we know our acceleration, and we know our time. We know that we started at 0 meters per second, but then we accelerated at 4 meters per second for 12 seconds. So that means that we must have reached a velocity of 48 meters per second by the time we stopped accelerating, which of course means that our constant velocity will be 48 meters per second throughout our whole second part of our trip. Okay, so now we can look at that last 15 seconds. We want to figure out what our second distance is. And we're going to use this equation here because in this particular section, there's no acceleration happening. So I'm going to use the equation that doesn't need acceleration. So our distance can be represented as 1/2 times the initial velocity plus the final velocity times time. Now, of course, our initial velocity and our final velocity are the exact same thing, so I really just have 2v times 1/2, which of course is just v, so I don't have to, I can just represent that by the velocity. So our distance is going to be the 48 meters per second that we were traveling times the 15 seconds that we traveled. So our change in distance will be 720 meters, which means our distance for the second part was 720 meters. So now we can look at what the whole journey was. We can see that delta x1 plus delta x2 would equal 576 meters plus 720 meters, which would give us 1296 meters. So our car traveled a total of 1296 meters. Now let's take a look at another question, and this one's going to be a little bit more difficult. It's going to take a little bit more thought. You're standing at the edge of a pier. You toss a stone straight upward. When the stone leaves your hand, it has an initial velocity of 10 meters per second, and your hand is about 5 meters above the surface of the water when you release the stone. What is the speed of the stone when it hits the water? So just like last time, we're going to start with a diagram to help us see what's happening. So we'll start with you on the pier. We have some water. You're going to throw a rock up, and it's going to come back down and hit the water. They've told us that your hand, where the rock, the rock leaves your hand, it's 5 meters above the water. But we don't know how high that rock is going to go before it stops moving upwards and starts coming down. We do know that its initial velocity, though, when it leaves your hand, is 10 meters per second. We also know that the velocity at the top is 0 because that's the moment that it stops going up and starts going down. The final velocity, which would be the velocity when it hits the water, well, that's what we're looking for. We do know that gravity is 9.81 meters per second squared. As I said, we don't know what the distance is in the up direction once it leaves your hand, but we do know that the down direction has got to be minus up minus 5 meters to give us our change in distance for the down. So our first step is to see how high does the stone go before gravity stops it. So we're going to use this equation right here because nowhere in this question have I mentioned time. So we want to use the equation without time. Velocity squared minus initial velocity squared equals 2a times our distance. All right, so we know that we can rearrange this to solve for our distance. So we can say that our distance is our final velocity, which is 0 meters per second squared, minus our initial velocity, which is 10 meters per second squared. And then on the bottom, we're just going to multiply our gravity by 2. So if we multiply this out, we're going to get a distance of 10.2 meters. So now we know that our up is 10.2 meters, which means our down must be minus 10.2 meters minus another 5 meters. So now we have enough information to solve the second part of the problem. How fast is the stone moving when it hits the water? So we're going to use the same equation, and we're going to solve for this here, our final velocity. So we'll rearrange this to solve for that. And we know that because this is at the moment when it stops going up and starts going down, the initial velocity is 0. So we can actually ignore that last term. So we have that velocity squared is going to be 2 times gravity pulling down, and we're going to be traveling minus 15.2 meters down before we hit the water. So in order to solve for that, we just take the square root, and we're going to be left with 17.3 meters per second. So not that difficult, but it did take a lot of sort of breaking apart the problem, and the picture definitely helped. So this is the biggest thing when it comes to solving questions like this, is the picture makes a huge difference. But as always, write down what you want, write down what you have, look at the equations. In this case, I didn't have time, so I had to use that equation. And then I used it for both parts, so I only really needed the one equation. Now, what I would like to do in this video was show you the examples of questions that use both horizontal and vertical motion. But I didn't want to make the video too long, so I'm going to leave that for next time. So next time we'll be talking about projectile motion. So if you found this video helpful, go ahead and hit like, and if you would like to see the projectile motion video, which will be coming soon, go ahead and hit subscribe and look for the next video.